Welcome back, sir. Sharath, sir.
Yeah, sure. Thank you. So let us resume. So here we just discussed on how we can achieve topic modeling using an algorithm called LSI or LSA, both means. What we are basically trying and doing is we have a very large Word document. Let's say some sentences we have, right? Out of these sentences, how can we extract a term or how can we map a term to this document? So we will see an approach of this algorithm. We'll see a small sample on how certain keywords will basically give us a text document or retrieval can be achieved. Now, in order to do that task, we need to understand a concept called as SVD. SVD is also known as singular value decomposition. This is a dimensional reduction concept, right? We are trying to reduce the dimensionality of the data because if you talk about a document or a corpus, we will get a huge DTM. There would be a huge number of words that we extract, right, from multiple documents. So this will become a large sparse matrix. Large sparse matrix. Sparse means empty. And when we say large matrix, let's say first document, document 1. Let's say this is a product review. So first customer is giving us a review and his review will contain some words, right? Certain words are there. So we will mark those words, right? Like this. Then we will take document 2, second document. In the second document, that is the second person's review, we may see completely new set of words, right? Or maybe there is word 1, but you have completely different set of words here in second review. So all these things will become 0, and here you'll get 1, 2, 1, like that. And for first document, these values will become 0. And different people will use different vocabulary, different way to express their feedback. So this matrix that we are getting here will become a large matrix. Hence, we need to reduce this matrix to a smaller form, right? And that reduction, dimensionality reduction, is happening using this SVD technique, singular value decomposition. And what does this do is, it is converting that matrix that we have, DTM, that we have, into 3 separate matrices. U sigma V transpose, you can also represent U D V transpose like this. Matrix multiplications, right? So let us try and understand first the basics of matrix calculations. If I talk about matrix operations, very simple. A matrix is a 2-dimensional array, 2-dimensional data, right? Data object. That means it will have rows and columns. A vector will have a 1-dimensional data. So here you will have 1 row, but you'll have 2 columns. If I say 1 comma 2, 1 row, 2 columns. So the dimension of this particular matrix is represented as 1 by 2, row by column. And if I apply transpose, then row become column and column will become row. So this becomes 1 by 2. So now I'll have 2 rows and a single column. So the dimension here becomes 2 by 1. 1 by 2 will convert to 2 by 1. If I have a 2 by 2 matrix, then the dimension will be 2 by 2, right? I mean, the 2 rows, 2 columns, then it is a 2 by 2 matrix. Now, when we talk about matrix, remember matrix multiplication is a tricky proposition, right? We need to do matrix multiplication, and this will become a tricky proposition. Now, let's say I have two matrices, A and B. Let me write this. 1, 2, 3, 4. Okay, this is a 2 by 2 matrix. Let's say B is, let's say 1, 2, 3, 4, 5, 6. So this becomes a 3 by 2 matrix, right? Now I want to do a matrix multiplication of these two. I want to multiply these two. That means I want to do A by B. So what would be the answer? We cannot do matrix multiplication if the column of the first matrix is not equal to the row of the second matrix, right? Will not be able to do the matrix multiplication. This cannot be possible. These two should be similar. But if I do transpose of B, if I say B transpose, then I would get 1, 3, 5, 2, 4, 6. So row becomes column, column becomes row. So here you will have 2 by 3, and your A is a 2 by 2 matrix. So now this 2 and this 2 are matching, the dimensions are similar. So I will be able to do the multiplication. So I say A multiplied by B transpose, or if I don't want to do transpose, then in this space I can do B multiplied by A. A multiplied by B is not possible, but we can do B multiplied by A. So B is 3 by 2 dimensions and A is 2 by 2 dimensions. So this and this are similar. We will be able to do the multiplication. And the end result will be 3 by 2. Here also, if you say these two are similar, so the end result will be 2 by 3. How do we do the calculation? The row of the first matrix multiplied by individual values of the column of the second matrix. That means 1 multiplied by 1 plus 2 multiplied by 2. This is in the first cell. Again, first row, second column. 3 into 1 into 3, then 2 into 4, 8. Similarly, first row, third column. How much is this? 5 plus 12. 70. So this way we do the matrix calculation. Again, 3, 4, the second row of this matrix with first column, second column, third column, that would give us the matrix multiplication. This is something that we need to remember from the matrix school days. Then we also have something called as orthogonal matrix. We have something called as orthogonal matrix. The orthogonal matrix has certain properties. Okay, and I'll just show you the example of the orthogonal matrix, which is very popularly used. 2 by 3, 1 by 3, and 1 by 3. Okay. Then minus 2 by 3, 2 by 3, 1 by 3. Then I'll say 1 by 3, 2 by 3, and minus 2 by 3. This is minus. Right. So this is basically our data that we see, right? And when you talk about this particular data, right, you take sum of any right, column, it would give you 0, or some of the rows will give you 0. This is 0, this is 0, and this should also give you 0. Okay, this is basically some mistake in my writing. Okay, this is -2 and 3. And yeah, this could be 1. Something like that. Fine. So if you look into the sum of the rows and sum of the columns, it will always be equal to 0. And this is the first property. And the second property is sum of the squared values should give you 1. So for example, if I take this column, 2 by 3 whole square plus -2 by 3 whole square plus 1 by 3 whole square. If I do this, this is 4 by 9 plus 4 by 9 plus 1 by 9. This is how much? 9 by 9, which is equals to 1. Right? And if you add these, this basically should give you a result as 0. Right? So that's basically how this right, algorithm is being written. Some of the values will have to be 0. Any 2 pairs, okay? Not all, but if you take any 2 pairs, the rows, then it would give you some of those values as zeros. Or you can also take some of the columns, it will give you the zeros. So for example, I comma j, if you add, this is I, this is j. When you add, you should get 0. Right? So that's basically how it is defined. Right? And yeah, probably somewhere I'm went wrong, but this is the properties. The properties of orthogonal matrix basically says you take sum of the squared rows, any 2 rows or any 2 columns, then value will always be equal to 0. And if you take sum of the squared values of a single row or a single column, it will be equal to 1. Column basically, single column will be equal to 1. These properties, right, basically are properties for orthogonal matrix. These are something that we discussed in school days. Basic properties I'm talking about. Right? Now, when you perform SVD, it does this conversion. It decomposes your data into 3 different matrices. U, V transpose. Right? And U and V are orthonormal matrices, that is, they are orthogonal matrices. And the sigma that you're seeing at the center is called as a diagonal matrix. It's called as a diagonal matrix. So these are some of the basic matrix multiplications in R. Right, so I'll do help. These are the matrices related applications. This is R programming. And I'm defining a matrix here. And you can see A is 1 by 2. If I apply transpose, it gets transposed to a vector, a matrix of 2 by 1 dimension. Right? So this is how we can do the matrix calculations. And this is matrix multiplication. So I have 3 by 2 matrix, and then a matrix B, I'm creating it as a 2 by 4 matrix. So this is 3 by 2, whereas this is 2 by 4. And for matrix multiplication, we use the symbol percentile star percentile. And this gives us a matrix which basically is going to be a dimension of 3 by 4. 3 by 4, because this is 3 rows and this is 4 columns, we get 3 by 4 dimension matrix. Right? So that's basically how we can do matrix multiplication. And yeah, let's not worry about orthonormal matrix. We'll try and look at something called as eigenvector values or eigenvalues. So eigenvectors and eigenvalues, right? Very simply, I'll try and explain. If this is a vector, okay, A is a matrix and I have vector V, then I can represent this matrix using eigenvector and eigenvalue, right? Like this, with this representation. So this vector that you're seeing is called as eigenvector, and this is called as eigenvalue. For any matrix, we can represent this, right, in this way, the data in this way. And we can have multiple vectors and multiple, you see, values. Different vectors and different values can be there. So here I'm creating a 2 by 2 matrix, a square matrix. This is A. If I apply eigen to A, then it gives us results which are eigenobjects. You can see eigenvalues and eigenvectors. So there are two eigenvalues and eigenvectors that are captured. You can separately capture eigenvalue 2 and 0.5, and you also have eigenvectors. What does that basically mean? Let me show you. So my matrix is this, right? This is your matrix. So I have 2, then I have 0, then I have 0 and 0.5. Yeah, this is my matrix, 2 by 2 matrix. I will take eigenvector, right? Let's say I will take this vector to start with. -1, 0. And this can be represented using an eigenvalue 2 into the same vector. I can represent like this. So if you multiply these two, what I'm getting? Row, column, right? -2 and 0, 0, 0. So I get -2 here when I do the calculation. So this is 2 by 2 and this is 2 by 1. So what I'm getting? I'm getting a result which is 2 and 0. Right, this is the result that I'm getting. If I multiply this constant, I'll get 2 and 0 only. You can also have 1 and 0 here. This is also eigenvalue and eigenvector. You get same result. If you multiply, if you see, you get the same result. Right? So this way you can have different eigenvectors and different eigenvalues. These are basically transforming your data into these vectors and right, values. So SVD is a technique which is applied on matrix to reduce the dimension by doing, right, approximation. Okay, so we are basically doing approximation on SVD. So what we do is, let's define this matrix. This is your matrix, and I'm just randomly creating some matrix. On this matrix, I would apply SVD. Now, when you do SVD, your original matrix is getting converted into 3 different matrices: U, D, V transpose. Now, in our LSI algorithm, you can look at this image. This is your X, which is of dimension M by M, assume. DTM, this is your DTM, right? Or TDM. We are converting that, if it is TDM, we are converting it into terms to topics. Okay, basically we are getting terms. And topic importance. When I multiply these two, this is like U, this is diagonal matrix, and this is V transpose. When I multiply these two, these are same, so I get M by N terms matrix. Right? I get terms matrix. And when I multiply these two, I get topics. Right? I get topics. So I get terms and then I get documents or topics. But rather you can say documents. If I multiply these two, I get n by n, right? This is the matrix. So here I get documents. Okay, so what we do is we take terms, we multiply these two, we take terms and we use a query. Okay, search query. So let me show you a small example here. So this is a search. Okay, I'm doing a query, very popular example, dice and dagger. I'm searching in Google for dice and dagger. If I do the search on this text data, document search, I should probably be getting the first result as D3. Because I have die, I have dagger. Excuse me. Sorry. Right? This is the first result. That means when I do the search, I should get document 3. If I do a search using these keywords on these documents, Romeo and Juliet, Juliet, oh happy dagger, Romeo died by dagger, live free or die. That's the New Hampshire motto. Did you know New Hampshire is in New England? New Hampshire is in New England. So these are the 5 different sentences that we have or documents we have. And I'm doing a search using a query key. Right? So in Google, if I do that, then what is the result that I should get? If I simply look into the keyword search, keywords, then what would I get? D3 as the first result, because died and dagger both are there. Then probably dagger. Then probably D4 because I have died. This is irrelevant. This is irrelevant because I don't have either of those keys. So I will say D2 and then D4. This is the order in which I should get the results if I use keywords. But we are using LSI, right? So we apply SVD to decompose that particular DTM or TDM and then give indexing query value to the terms. So on this particular document, if I have 5 different documents, I would take TDM on top of that. So Romeo, yes, it is there. Juliet, it is there. Right? Romeo and Juliet. Both these words are there in the first document, D1. Right? This D1. I have Romeo and Juliet. The rest of the words are not there, so I'll put zeros there. Then in document 2, I have Juliet. I don't have Romeo. I have Juliet. I have happy. I have dagger. Then D3, Romeo is there, died is there, dagger is there. Dagger and died. D4, I have live, die, free, and New Hampshire, right? Hampshire. So I have these 4. And D5, I only have New Hampshire. None of the words are there. So this is your TDM and that weightage. Right? Now, using this as an input, we would have to perform SVD to convert that into 3 different matrices, right? So let us first try and show you what happens when I do SVD on this example matrix. So if I apply a SVD, SVD object will contain 3 different components. SVD object, you can see, consists of 3 different, right? List of 3 different objects. D, U, and V. So U is this matrix. D is a diagonal matrix. That means only on diagonal you have values. Rest of the values will be zeros. right? And we have V, and we take V transpose on this particular matrix to get the X back. So you can see here, if I apply U multiplied by diagonal matrix of D and then transposed of V, if I do that, I should get X. This is the product, and if I say X, which I define, you can see both are same, right? Both these are exactly same. So now I'm using this example here, which has 5 documents, and if I do the query, then what is the result that I'm getting, right? So I'm trying to load the matrix. In Excel, we have seen this TDM, right? This TDM is what I'm creating here as a matrix. If I search for A, if you see only A, you will get that matrix, but you will not have terms or the headers. So I'm giving column names as D1, D2, D3, D4, right? And you can see again A. You'll have the column names assigned. Now I'm also giving row names. Row names are nothing but these names that we have, right? The terms. So manually, right? Manually filling it up so that you can understand what we're trying to do here. So if I say now A, the same Excel that we have seen, the matrix that we have seen, the TDM is available here. Remember, it's a matrix. I am decomposing this using SVD. And when I say SVD, we have seen that this A, matrix A, is decomposed into U, V, and U, D, and V transpose. U is a term to topics matrix, terms to topics. That means it will contain the terms, words. And then topic importance matrix is also captured, which is a diagonal matrix, topic importance. And then topics to documents is something that we have in the V transposed calculation. So this is U. We can see this is the result that we get. And diagonal matrix, if you see, this is the diagonal matrix. Only diagonal will have the values. And then V. If you see V transposed, this is the V transpose. So if I multiply all these three, we get original matrix back. That's SVD technique. Now, dimensionality reduction is applied by approximation. So here we are doing rank to approximation. When I say rank to approximation, we are taking the first 2 columns of U. Then we are taking your diagonal matrix, right? 2 rows, 2 columns. That is diagonal matrix, right? So you'll only take the diagonal values. All right?
Including yes.
So we have U, we have diagonal matrix. I'm taking only approximation 2. We can also take approximation 1. If you look into SVD technique, okay, this is the approximation, SVD approximation. Here I'm taking approximation 2. This is my original U sigma V transpose that we have seen, right, in R. On this, when I say approximation 2, then we'll take 2 columns of U, 2 diagonal values of your diagonal matrix, and then in the V transpose, we take only 2 rows. The dimension will be same, but we will be able to achieve compression here. If you see, huge compression is what we are achieving, right? Same way, we are doing rank to approximation here. So I'll take U2, which will be only the two columns of your U matrix. Then I'm taking diagonal values 2 by 2. That means I only consider these 2 by 2 diagonal values. And in V transpose, I take 2 rows. Right? So I have 2 columns, 2 by 2 diagonal matrix, and 2 rows. Now I'm taking the terms by multiplying these two. How many words we have here? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 words. So you see here, we will get 8 words values. So we're getting weightages for 2 words. Sorry, 8 terms. Right? I'm doing a 2 by 2 matrix multiplication here with U2. That is 2 columns. 8 rows, 2 columns. So if I have to write the dimension here, I get 8 rows, 2 columns, rank 2 approximation, multiplied by 2 by 2. This is common, so I would get 8 by 2 approximation. Now, similarly, I will be doing multiplying of these two to get documents. These are the words. Right here I'm doing documents. So I have 2 by 2. This is S, the diagonal matrix. And then V transpose. Right? V transpose is 2 by 5. V is 5 by 2, but we transposed it, right? So these two are similar. So I get 2 by 5 as a resultant document. So this talks about documents. So we are getting the terms and we are also getting documents. Now we also have to see the query. We need to look into the query, right? What is the query that we are making? The query is dice and dagger. So dagger is in the 4th position, whereas die is in the 6th position. So I'm taking 4th position first, dice and dagger, right? So 4th position plus 6th position and doing average. Right? This is your query result. And you get this result. So you take terms. Terms is your this data, right? Term document matrix. You have terms, which is this. So you take 4th value and you take 6th value and do the average of these two. You get this result. Right? So 4th and 6th, when you average, you are getting this result. Now to get the ranks on top of this data, we are creating a matrix. First, create a null matrix. You might want to see what is the ranks here. This is a result which we have for getting the ranks on that particular matrix. Okay. Now, to get the ranks for each row in the ranks, what we are doing, we are taking some of the documents multiplied by query divided by square root of this calculation. So what we are basically doing here is we are checking the similarity. You can see this is cosine based similarity that we are applying. Cosine based similarity between the, you can say, document and the query. So this is dot product of document and query, then ampersand modulus of D and modulus of Q. So this is summation of D and Q divided by square root of DI square, summation of DI square, multiplied by square root of summation of QI square. That means q1 square plus q2 square plus q3 square, so on and so forth, right? So that's what we are trying to do here. If I do this calculation, I get the ranks for each and every document with respect to this particular query, right? So we are taking one document as a vector, query as a vector, and then we are measuring the similarity. And when I do this, this is the ranks. So what do we get here? Highest rank is for the third document, that is Romeo died by dagger. This is fine. Then the second most popular or highest rank is document 1. If I used keywords, then I should probably be getting second one as the result. But if you observe here, the second result is for document 1, Romeo and Juliet. But if you observe, I don't have dice, I don't have dagger in that particular document. Isn't it? But I get that Romeo and Juliet as the second highest result, because it is relevant to that subject, dice and dagger. Romeo and Juliet, if you know the story, then you understand the correlation between Romeo and Juliet. So context is something that we are trying to extract. So this is how we can perform LSI. So just to summarize, right? Let me just summarize the things that we have done here. I'll write it here in the empty space. We took documents from the corpus, and from that we created a TDM structure. This is unstructured data. We structurized it. Then we performed SVD to decompose this. Right? We got the TDM into 3 different matrices. Then the fourth step we performed is rank to approximation to get this big matrix to compress. Right? So this is rank to approximation. We call it as rank to approximation. Then the fifth step that we did is multiply document with, sorry, my bad. We multiplied U with diagonal matrix. This gives us the terms matrix, right? Terms to topics matrix, the terms basically. Then we also did D multiplied by V transpose. This gives us the documents. Then we took the query term, dice and dagger, right? We took that query's weightage from the terms matrix, and then we performed cosine based similarity between documents and the query term. This gave us the ranks, and based on the ranks we publish the documents. So LSI, latent semantic indexing. So we are trying to extract hidden pattern. Latent means hidden, right? So we're trying to identify hidden patterns by doing the indexing to the documents. So this is about LSI, topic modeling concept in textual analytics. Do we have any questions? Any questions?
No questions.
Hope the concept is clear.
Yes, sir.
Even if you did not understand coding, that's okay. The concept is more important. Okay. All right. So yeah, if you have no questions, then hope you enjoyed the session. I would definitely like to have feedback. Yeah, I'm privileged to have esteemed participants here. So if you have any feedback, please you can be very vocal. I would love to hear from you.
Sir, your talk is absolutely fantastic, sir. If it is possible, please share your email ID and contact number, sir. I want to contact with you because I am working on a time series for custom and I want to integrate this natural language processing in predicting the future data also.
Oh,
So
wonderful.
it would be nice, sir, if you will provide your email ID so that we can communicate with each other.
Yeah, definitely I'll do that. I've shared my LinkedIn profile.
Yes, sir. I have already sent a request to you, sir.
Yeah, I'm very active on LinkedIn. You can directly connect with me on LinkedIn. My number should be there on LinkedIn also. If not, I can leave a message there. I think I've already connected with you on LinkedIn.
Thank you, sir.
Thank you very much, Sharath sir, for the excellent session and
My pleasure.
giving time from your busy schedule and taking such a wonderful session. Such feedbacks are there in the chat box. You can see, Sharath sir.
Yes. I'm excited. I'm very happy.
Okay.
Thank you so much. Thank you so much.
Okay. Thank you, sir. Thank you once again. Thank you
My
for that.
pleasure.
Okay.
Thank you all, and yeah, see you soon again. Thank you.
Okay. Thank you, sir.